All right, last time we left off looking at what are probably the most heavily studied organic reactions of all times, the aldol reactions, specifically the aldol addition. The aldol addition is wildly important synthetically. It's a reaction that makes carbon-carbon bonds, and that means you can take relatively simple molecules like aldehydes and ketones, couple them together to make a carbon-carbon bond, making a beta-hydroxycarbonyl compound. The new bond that's formed in the product is between the alpha carbon and the beta carbon, which has that hydroxy group on it. Not only is this really important synthetically, it's also really important biologically. For example, let me show you this. Here I've got a simple sugar molecule, glucose. And if you look carefully at the structure of glucose, you can see, well, it's got a carbonyl. And on carbon 1, you get the carbonyl, carbon 2, and then carbon 3. Now, carbon 3 is beta to that carbonyl. In other words, glucose, like most sugars, is a beta-hydroxycarbonyl. It's an aldol addition product. So glucose can be metabolized by transforming it into a phosphorylated version of fructose through some simple oxidation chemistry, really. But notice that fructose itself, look at carbon 2, that's a carbonyl. Then carbon 3, carbon 4. Carbon 4 is beta to carbon 2, and it has a hydroxy group. Again, fructose is a beta-hydroxycarbonyl. It's an aldol addition product. The way the body metabolizes sugars, if you look here, I've got it kind of color-coded. That red bond is between the alpha and the beta carbon relative to the carbonyl. That bond could have been made from an aldol addition. What the body does is it uses an enzyme, aldolase, to undo that bond. It breaks it through what's called a retroaldol reaction, giving us two carbonyls. Here I've got it in blue and green. So the blue molecule would be enolized, would then attack the green aldehyde, a glyceraldehyde, forming that red bond, making an aldol product. That's basically how the body metabolizes sugars. And of course, the reverse process is taking these simple little 3-carbon chunks, like pyruvates, and doing aldol chemistry on them to make sugars. And that's photosynthesis, probably the most important reaction of all. All right, so we left off looking at a few variations of aldol chemistry, like the mixed aldol and the intramolecular aldol to make cyclic structures. What we're going to start looking at today is what happens when you start making enolates and reacting them with other types of carbonyl compounds other than aldehydes and ketones. Remember, aldol addition is an acyl addition. You form an enolate, which acts as a nucleophile, and that reacts with an aldehyde or a ketone as the electrophile. And of course, aldehydes and ketones do electrophilic additions. That's why you make alcohols in the aldol addition reaction. But what if we made an enolate from a molecule that then reacted with a different kind of a carbonyl? Let's say an acid derivative. Well, that's exactly what the Claisen condensation is. So here, I've got two esters, admittedly the same ester twice, kind of like what I showed you with the aldol addition earlier. You wouldn't normally draw it out this way. You would normally just draw out the ester once, but I think it's easier to envision what's going on if you see it drawn twice. Because what we're going to do is we're going to react one molecule of this ester with another molecule of the same ester. And again, it really relates back to the aldol chemistry we saw before. Some of this ester molecule is going to get enolized under basic conditions. Here's the enolate, and then it attacks the other ester, the one that didn't get enolized. Now, because it's an acid derivative, remember that acid derivatives do acyl substitutions. So the enolate attacks in sort of the normal way, breaks the carbon-carbon or carbon-oxygen pi bond, forms a tetrahedral intermediate, which then collapses in the second step of the acyl substitution mechanism, in this case ejecting out the alkoxide, ethoxide, to make a carbon-carbon bond. But because the electrophile was an ester, which does acyl substitutions, and the nucleophile was an enolate, that's a carbon nucleophile, it means that the product is now going to be a ketone. Specifically, it's going to be a beta-keto ester, as you can see in the product here. The ester over here on the right, and then 2 carbons down the pipeline, you get to the beta carbon, and that is a carbonyl, specifically a ketone in this case. It's a really straightforward mechanism because all it is something you've seen before. With respect to the ester that's acting as the electrophile on the left, in that mechanism, it's just an acyl substitution. Just imagine any other nucleophile, like hydroxide or something like that, attacking, breaking the carbonyl pi bond, which then reforms and expels that leaving group. It's a really simple reaction, and it gives you a multifunctional molecule at the end of the day. Now, there is one little thing you've got to concern yourself with when doing a Claisen condensation, and that is typically you want to match the base to the actual leaving group, the alkoxy group of the ester. So here you notice that I'm using ethoxide for my conditions, and that's really important. If you try to use something really simple like hydroxide, the reaction would work. The hydroxide would be plenty basic enough to go ahead and enolize that ester. The problem, of course, is that hydroxide would also participate in acyl substitution as a nucleophile. In other words, you'd wind up getting hydrolysis. You'd wind up making carboxylic acids out of your esters because of a competing reaction. Using ethoxide kind of gets around that. If you matched the base to the leaving group of the ester, then if the ethoxide attacks the carbonyl carbon and does an acyl substitution, all that's going to happen is you're going to wind up replacing ethoxide with ethoxide, and you can't tell anything happen. So the only thing that can happen productively is the enolization, and that then can lead to the Claisen condensation products. Now, it is certainly possible, just like we saw with aldol chemistry, to have mixed or crossed versions of this chemistry. In other words, you can react two different esters together. Again, there's a problem with this in that oftentimes you wind up with lots of different possible products because one molecule could enolize and then react with another molecule itself. And, it's a big old mess. One of the ways we saw around that with aldol chemistry was to simply use only one molecule that was enolizable and then react it with another molecule that was not enolizable. It limited the products. And you can do the same thing here with a Claisen. It's not often quite as clean, but here in this example, you can see I'm reacting ethyl acetate with ethyl benzoate. And ethyl benzoate cannot enolize. While it has an alpha carbon in the benzene ring, that has no alpha hydrogen on it, so it can't get enolized. But the ethyl acetate can. So the only enolate can form is from ethyl acetate. It can then react with, well, technically another ethyl acetate or the ethyl benzoate. So that's the product I've drawn out here. Notice again that I have matched my base to the actual leaving group, so to speak, on the ester, the ethoxy group in this case. Another way around this, exactly like what we saw with our aldol chemistry, was to use something like LDA. You could take one of these esters separately, pre-treat it with LDA, and then react it with the other ester. Because you're using LDA and because that basically is never going to give that proton back, you quantitatively make one enolate, which can do nothing. It can't react with another molecule of itself because it's all enolized. And so it can only just sort of sit there and wait until you dump an electrophile on it, dump another ester on it, and then force that ester to react in a Claisen. Just like we saw with aldol chemistry, you can also have an intramolecular version of the Claisen reaction. This actually has a special name. It's called the Dieckmann cyclization. So here, think about it. What you're going to need to do an intramolecular Claisen is going to be two esters, right? One that gets enolized and one that acts as the electrophile. Again, this relates really, really nicely to what we saw with aldol chemistry. So here I've got, what is this, a 1, 2, 3, 4, 5, 6, a 6-carbon diester. And I've kind of puckered it around on itself so you can kind of see what's happening. Let's say we have this dimethyl ester and we treat it with methoxide to enolize it. Now, there are two sites for enolization, right? There are two sets of alpha protons. But in this molecule, because of the symmetry, it doesn't matter which pair of hydrogens rather we remove. So here I'm going to remove one of the hydrogens from that lower methylene, that lower CH2. So if we enolize there, then that enolate can react and attack that carbonyl up above, do the Claisen, do the acyl substitution, and in this case, close up a 5-membered ring. It's the alpha carbon from this bottom carbonyl attacking the upper carbonyl. And if you count that out, that's actually going to make a 5-membered ring. Again, notice that the product is a Claisen product. It is a beta keto ester. As long as you are sort of counting alpha, beta, gamma through the carbon-carbon bond that was formed between the alpha carbon below and that carbonyl up above. And of course, this has all of the same stipulations that we saw with aldols that were cyclic as well, right? You have to worry about what ring size you are making. In this case, it was pretty simple because you could only make one ring size. And with esters, that's more often than not the case, unless you have a really complicated molecule. You can only enolize one side of an ester, unlike a ketone that could potentially be enolized on two different sizes. But again, do pay attention to that kind of thing. Make sure you're making reasonable ring sizes through your chemistry. All right, so what's left? We've got carbonyls. We've got two classes of carbonyls. We've got aldehydes and ketones that do acyl addition, and we've got our acid derivatives that do acyl substitution. And you'll notice that I only really mentioned esters in that reaction of like the Claisen chemistry. While other acid derivatives can undergo acyl substitution and do some Claisen-like reactions, you rarely really see them. Carboxylic acids don't react because they would just get deprotonated on the actual OH group, right? That's way more acidic than the alpha hydrogens are on the enolate formation. So yeah, you almost really never see carboxylic acids participating in this kind of chemistry. Amides are just generally too reactive. The leaving group is too poor. It's really mostly restricted to esters and occasionally acyl halides. And that's pretty much it. So what's left? Well, there is one special class of molecules that can still react with enolates, and they're carbonyls that have alpha-beta unsaturation. So here I've got an alpha-beta unsaturated carbonyl. Now remember, with an alpha-beta unsaturated carbonyl, you have two sites of electrophilic character. You have the original carbonyl, an attack there we call direct attack, but we also have electrophilic character at the beta carbon because of resonance. And when a nucleophile attacks there, we call it conjugate attack or conjugate addition, because it is addition at that point. Well, all we're going to do is take that same concept that we talked about before in our last unit, the fact that alpha-beta unsaturated carbonyls are electrophilic at two sites. And if you recall, we had to kind of look at what kind of carbonyl it was and what the nucleophile was to figure out whether it was going to do a direct attack or a conjugate attack. Well, we're talking about enolates here, and that means that the nucleophile is going to be an enolate. Now, the electrophile part, the carbonyl, could be anything. Here I have a ketone. I could have used an ester, whatever. Because we are using enolates as our nucleophiles, these typically do the conjugate addition. And a conjugate addition of an enolate onto an alpha-beta unsaturated carbonyl is called a Michael addition. So here I've got this alpha-beta unsaturated ketone reacting with this diketone. Now, it doesn't have to be a diketone, but there are good reasons to do it that way, and I'll address that in a minute. Regardless, we're going to use hydroxide here as the base. You can use other bases, certainly. And we're going to enolize that carbonyl, that ketone. Now, this is a special ketone, right? There are three sites for enolization. There are three sets of alpha protons on this diketone. However, one of them is really special, right? That methylene in the middle. We talked about this before when we talked about the relative acidities of hydrogens on carbon. And when you have a carbon with a hydrogen that is flanked on two sides by carbonyls, it can create an enolate that is resonance stabilized over three resonance structures, making it really stable and therefore really easy to make. So when we treat this particular molecule, this diketone, with a base like hydroxide, it's going to basically quantitatively enolize because it's so acidic. And it's going to quantitatively enolize it in a very regio-specific way, right? It's going to go ahead and deprotonate between those two carbonyls. So that enolate can then react with our alpha-beta unsaturated carbonyl at the beta carbon doing a conjugate attack, just like we saw in the last unit. Here I've got the mechanism drawn out. The enolate electrons can flow through, attack that beta carbon. The electrons are pushed off of the carbon-carbon pi bond and then break the carbonyl bond, making, if you actually look at it, another enolate. And then that enolate is simply protonated by a solvent molecule or something like that at the alpha carbon. Now, in this particular case, you do wind up with a pretty heavily substituted, functionalized molecule. You can see I've got three carbonyls, three ketones specifically in this molecule. The Michael addition specifically gives 1,5-dicarbonyls. Again, I didn't have to start with a diketone as my nucleophile. I could have started off with a regular old ketone, but there's a good reason for this. In general, the weaker the nucleophile is, the more likely it is to do conjugate addition relative to direct attack on a carbonyl that's alpha-beta unsaturated. By having this particular kind of molecule, where we have two carbonyls flanking that CH2 in the middle, making that so acidic, the conjugate base, the enolate, is so stable that makes it non-reactive, well, relatively non-reactive. And that kind of guarantees that it'll do conjugate addition rather than a direct attack on the carbonyl. That's why you often see the Michael addition done with particularly stable enolates, like those generated from these 1,3-dicarbonyls. But regardless, if you look at the final structure, if you take one of those carbonyls away from the diketone, let's say we hack off this lower one here, you can see that the remaining structure has to be a 1,5-dicarbonyl. 1, 2, 3, 4, 5 to that other one. The extra carbonyl is just sort of fluff that we included to make the reaction, kind of guaranteed to go towards that conjugate attack. This is a really convenient way of making dicarbonyl compounds, right? This 1,5-dicarbonyl functionality pairing is something you should learn to recognize when you look at a product. If you see that, if you see two carbonyls with a 1 to 5 relationship in terms of where they are on the carbon skeleton, here's a good bet that may have come from a Michael addition. What we're going to look at next is really a combination of things we just talked about. In fact, again, I've said this before, that's really what this unit is about. Once you learn enolates and what they are and the fact that they're nucleophiles, just about everything we look at in this unit is just taking that new nucleophile, that enolate, and reacting it in old ways with electrophiles that we already know what they do. So next we're going to combine a couple of reactions together into something called the Robinson annulation. And you'll notice that I actually have the same reactants and reagents that I had in my example for the Michael addition. Here I've got an alpha-beta unsaturated ketone and this sort of double-flanked dicarbonyl kind of thing, this diketone here. So what happens in the Robinson annulation initially is exactly what happens in the Michael addition. We enolize one of the carbonyls, which then does a conjugate attack to create a 1,5-dicarbonyl. What's going to happen next, if you have just the right pieces in place, like we do here, look at it. This is a tricarbonyl in this case, right? And you're guaranteed to have a dicarbonyl when you do a Michael addition. Remember that 1,5-dicarbonyl product you get. Because you have multiple carbonyls on the same molecule, it sets up more enolate chemistry. Specifically in this molecule, I have 3 ketones. And what can happen is that one of those ketones can get enolized and react with one of the other ketone functionalities in the molecule to do an intramolecular aldol reaction. It can be a little tricky to figure out exactly where you're going to enolize, and it's not exactly conventional in the sense that, I have thermodynamic conditions here, so I'm going to form the thermodynamic enolate. You might or might not. Remember we talked about this when we did the cyclic version, the intramolecular version of aldol chemistry. Just because you have a weaker base like hydroxide that promotes thermodynamic enolization doesn't mean you're going to wind up actually making the thermodynamic type enolate, because it may not lead to a stable ring structure. It may be something like a strained 3-membered ring. So a lot of times you sort of have to play with it. If you look at the structure here from the actual Michael addition, we're going to enolize this methyl group right here. If you look, that methyl group was a part of the alpha-beta unsaturated molecule, away from the alpha-beta unsaturation, right, in the other direction from the carbonyl. And as long as you have that, as long as you have that carbon right there with a hydrogen on it, an alpha carbon with an alpha hydrogen on it, and you have that other carbonyl, of course, from the Michael addition, the one way up here, then this intramolecular aldol is going to be possible. So if we enolize there, which carbonyl is going to be attacked? Well, it doesn't matter, right? Because if you look at it, the 2 remaining carbonyls are actually the same. If you count 1, 2, 3, 4, 5, 6, they're both 6 carbons away from where we just enolized. So it doesn't really matter which one you attack. The way I have it drawn out, I've kind of made it easier to see it attacking that one kind of local on the page. So we just do an intramolecular aldol. Of course, there's no mechanism drawn here because it's stuff we've covered before. The Robinson annulation is nothing more than a Michael addition followed by an intramolecular aldol. And it usually goes through an aldol condensation. Again, we have these thermodynamic conditions that tend to promote the dehydration step, and 6-membered ring formation also tends to promote that dehydration. I think I may have mentioned that before. The product here is a clunky one. It's got a lot going on, right? You have this new 6-membered ring, and you will always make a cyclohexenone with the Robinson annulation. So you've got the 6-membered ring, it's got an alkene in it, which is part of an alpha-beta unsaturated ketone. And then you also have this other chunk 4 carbons away on the ring, that other carbonyl. This is not one that's just easily memorized. You've really got to kind of plan it out and plot it out and draw it in pieces to really get these reactions under your fingers, I think. But really fundamentally, there's nothing to it. There's nothing new here, in other words. It's just a combination of 2 things we just talked about. A Michael addition followed by the intramolecular aldol condensation. You might be wondering, well, why didn't I do a Robinson annulation when I talked about the Michael addition? Because it's the exact same molecules and the same reagents. Yeah, I could have, and it probably would do the Robinson annulation. When doesn't it do a Robinson annulation is an often asked question. And typically, my general thought on it is it'll probably do the Robinson annulation if it can. So when can't it? Well, when you don't have those alpha hydrogens on the other alpha carbon of your alpha beta unsaturated carbonyl. So in this example, you see I'm starting with a methyl ketone on one side, and of course that double bond, that alkene on the other side. That's part of my alpha beta unsaturated carbonyl. What if I didn't have that methyl group there? What if instead I had a methoxy group? Well, that would make this an alpha beta unsaturated ester. That's fine. It can still do the conjugate addition. That's not changed. But once that occurs, you no longer have a methyl group here. You have a methoxy group in that product. And the methoxy group has no alpha protons there, which means it can't enolize, and it can't make that nice stable 6-membered ring. You might be able to enolize somewhere else. The problem there is you're going to wind up making really clunky ring structures if you try it. I mean, take a look. If I try to enolize the other side of this structure, above the carbonyl, well, if that were to attack one of the two other carbonyls, what would I get? 1, 2, 3, 4. I'd get a 4-membered ring, and that's really highly strained. It's going to pop back open again. So that's when the Robinson annulation doesn't happen, when you really are lacking alpha protons on the other alpha carbon of your alpha beta unsaturated carbonyl. Had I started with a alpha beta unsaturated ester, yeah, it would just do the Michael because it couldn't go further. It doesn't have the ability to do this enolization step. All right, so now for something completely different. What we're about to look at is something that actually relies on enolate chemistry, but in a really strange kind of way, one that you wouldn't predict. We're going to look at two reactions that are called decarboxylations. And they take a very specific set of functionalities to actually allow this to occur. So here I've got, if you look at this, this is a dicarbonyl. Specifically, it is a beta keto acid. The keto part isn't really all that important. What you really need to have is any kind of a carbonyl, beta to specifically a carboxylic acid. It has to be exactly a carboxylic acid. So we have that here. And this can be done under either acidic or basic conditions. So what happens, if you look at it, is that we basically break off that carboxylic acid functionality and replace it with a hydrogen. If you do the math there, you're basically removing carbon dioxide, which is why this is called decarboxylation. You're removing the carboxylate group, essentially. So it collapses down, and you wind up just putting a proton, a hydrogen, in its place. This is another interesting example of a carbon-carbon bond breaking reaction, very much like what we saw the other day with the haloform reaction. And this can, again, be somewhat synthetically useful. You can kind of maybe have some easy chemistry, some very simple pattern that makes the molecule you almost want, but it has one too many carbons, and then you just sort of bubble it off as carbon dioxide through a decarboxylation. So let's take a look at the two mechanisms for the acid and the base-promoted versions. They're actually quite a bit different. So here's the acid-promoted mechanism. You'll notice that the molecule has to kind of wrap around on itself. It's, in a sense, kind of intramolecularly acid catalyzed. We've got this carboxylic acid functionality here. And if the molecule wraps around on itself, it places that acidic hydrogen right where it needs to be for the beta carbonyl to grab it with one of its lone pairs. What essentially happens is the lone pair from that other carbonyl, the ketone in this case, starts to create a bond with its lone pair from the oxygen to the hydrogen. Once that bond starts to make, you actually have a transition state that is a 6-membered ring, and that's a stable ring size. As that oxygen to hydrogen bond is made, of course, hydrogen can only maintain one bond, so the HO bond on the carboxylic acid has to break. Those electrons flow towards the electron-deficient carbonyl carbon, which then exceeds the octet rule there, pushing electrons back over to the original carbonyl. When you follow all that, it's a one-step mechanism. That's it. It's a lot of arrows flying around, and it's not the most conventional mechanism in terms of predictability, like nucleophile and electrophile type stuff. But the product you'll see is actually not a ketone, it's an enol. But we know that enols are actually unstable and will immediately tautomerize, typically, into their carbonyl tautomer. And that's exactly what happens here. So the acid-promoted version, really the acid can come from itself, from the actual carboxylic acid. The molecule wraps around on itself, does this strange sort of cyclic flow intramolecular reaction, and makes an enol that then tautomerizes into the carbonyl. And of course, CO2 is bubbled off as a byproduct. Now, this same chemistry can be done under basic conditions, but the mechanism is actually quite a bit different. It's a little bit more intuitive, I would say. So here we've got, again, you have to have a beta carbonyl relative to a carboxylic acid. Well, when you treat this with a base, naturally what you're going to do is remove the acidic hydrogen, the carboxylic acid hydrogen. So your base will remove that, make a carboxylate, and now that carboxylate can form carbon dioxide by pushing its electrons from the negative oxygen to the carbonyl carbon and push off the carbon as a leaving group. It's almost like an acyl substitution, really. It's kind of weird. Now, again, you wouldn't normally go around breaking carbon-carbon bonds, especially to make a carbanion. But if you look carefully, the carbanion we formed here is an enolate. It's just the less commonly drawn resonance structure of an enolate. But yeah, of course, it has the other resonance structure. This is no ordinary carbanion. This is a resonance-stabilized carbanion. It's really an alkoxide. It's an enolate, right? Anyway, it will then get protonated on the alpha carbon through a simple acid-base reaction, and there you go. You've bubbled off CO2, and you've made the same carbonyl. All right, so what we're about to look at next are some chemistries that actually rely on this idea of decarboxylation. And this is yet another example of nothing new at all. This is just taking stuff we already know and kind of packaging it together. I would hesitate to even call these reactions. These are almost just really common synthetic strategies. In fact, that's kind of how they're named. The first one we're going to look at is called the acetoacetate synthesis. And you would think that something called the acetoacetate synthesis would make something like an acetoacetate. No. It actually reacts acetoacetates, and the products are, in fact, ketones. So here I've got what's commonly referred to as an acetoacetate. And you can see how this name came about. If I cover up this side of it, you can see that it's really just acetone. And if I cover up the other side of it, well, that's just, in this case, ethyl acetate. So it's an acetoacetate. It's an acetate that we've kind of attached an acetyl group onto. Regardless, it's a difunctional molecule. It's got a ketone, it's got an ester, and it's got those really special acidic hydrogens in the middle because of that 1,3 relationship between the two carbonyls. So we can treat this with a modest base, and we know exactly where this is going to enolize, and it's going to be a very easy enolatation. So the first thing that happens, you treat this with base, and again, because I have an ester, I want to make sure to match that ester, the base with that ester's leaving group, in this case, ethoxide. And what we're going to do is an alkylation. We learned about alkylation a couple lectures ago. The base is going to form an enolate. The enolate will then attack. In this case, I'm using, 1-bromopropane. It'll react with 1-bromopropane and is what is really an SN2 reaction and introduce this alkyl group. From there, we're going to take and do an acyl substitution, specifically a hydrolysis reaction on the ester. We're going to hydrolyze that ester under acidic conditions, and we're going to form a carboxylic acid. And look at what we have there. We've got a beta keto acid, exactly what we need to do a decarboxylation. So the decarboxylation happens, the acidic catalyzed version of this, and you wind up bubbling off CO2. And if you look, this is just a sort of strangely drawn ketone. The acetoacetate synthesis doesn't make acetoacetates, it reacts them, and it actually makes elongated ketones. Here we started off with essentially a 4-carbon chain. We hacked off a carbon, right? We lost that carbonyl carbon from the carboxylic acid, well, ester group, it becomes a carboxylic acid, and then kind of replaced it with this 3-carbon chain from an alkyl halide. This is just a synthetic strategy, a way of making long-chain ketones, essentially, starting from some really cheap, available, easy reagents and simple chemistries. A very related synthetic strategy is referred to as the malonate synthesis or the malonic ester synthesis. And it starts off with a malonic ester. So this is what a malonic ester is. It's a dicarbonyl compound. It's actually the ester of what's called malonic acid. It's a diacid. So here I just have diethyl malonate. But again, you notice that it's got that 1,3 relationship between the two carbonyls, meaning that we have those really highly acidic hydrogens on that methylene carbon in the middle. So again, we treat this with a base, making sure to match the base to the leaving group of our ester, ethoxide in this case. We're again going to do an alkylation. Here I'm just going to use bromomethane. We're going to introduce a methyl group there, and then under acidic conditions, hydrolyze that ester to a carboxylic acid, which would give us a beta keto acid, and that allows us to do a decarboxylation. It's really the same exact thing, except because this is a diester, you wind up hydrolyzing both esters, removing one of them essentially as carbon dioxide, giving you now a carboxylic acid as the product. The malonic ester synthesis reacts malonates and creates long-chain carboxylic acids. Again, overall, you're starting with a 3-carbon chain, losing a carbon to a 2-carbon chain, and then kind of replacing that carbonyl with another alkyl group, in this case, just a simple methyl group, because that's what I used. I used bromomethane. But you can use pretty much any primary or methyl alkyl halide as your alkylating agent here to introduce whatever carbon chain you really want. All right, that's going to wrap it up for this unit. All this enolate chemistry is pretty darn simple. There aren't that many things we covered. We introduced what an enolate is, how they're made, either through base conditions or under acidic conditions to make enols. But we really didn't do a lot with enols aside from that one halogenation reaction. Generally speaking, this whole unit is basically just taking a new nucleophile, an enol or an enolate, and doing old chemistry with it. You react an enolate with an alkyl halide, it's going to do an SN2 reaction. We call that alkylation. You react it with an aldehyde or a ketone, it's going to do what aldehydes and ketones do. It's going to do an acyl addition. We call that aldol addition. You react an enolate with an acid derivative like an ester. Esters do acyl substitution, so that's what it does, and we call that a Claisen condensation. You react it with an alpha-beta unsaturated carbonyl. It's going to wind up doing a conjugate addition. We call that a Michael addition. Really, the only thing terribly new, aside from introducing what an enolate is, which technically we've seen that before, is this decarboxylation step, right? This decarboxylation chemistry that goes through enols and enolates as intermediates, but can also be useful in some synthetic strategies for making long-chain ketones and long-chain carboxylic acids. So what confounds students about this material is that it is often multiple carbon chunks, multiple functional groups, 2 ketones or 2 esters, or the Michael addition in particular. You've got a difunctional molecule, an alpha-beta unsaturated carbonyl, and then another carbonyl. And bringing them together, that's what usually confounds people, because you wind up with 2 carbon chunks to start off with, and you're combining them up into what is often multifunctional products. But don't get lost in the weeds. Just look at it as simply as I just tried to describe it. It's literally just taking a new nucleophile and reacting it in old chemistries. There's almost nothing new in this unit aside from the decarboxylation.